P to the 1 equals 1 factorial of 1 is 3 times e to the minus 3. We already knew what e to the minus 3 was, 0.05. Look, you know, I said it's slightly lower. So then the next one is going to just be 3 squared over 2 factorial is the ratio. That's 9 over 4. 9/4 of e to the minus 3. Yeah, you can keep going, but you can plug it in. I did that one fast, didn't I? 2, 3, and then that didn't change, squared over 2 factorial. Oh, I didn't have 1, 4, it's 2, sorry, right? Or no, yeah, e to the minus 3. That should be 9 tenths. Made a mistake there. Why do we do that? Yeah, confused. I'll be worse than a few graphs. So that's how they got that, added it all up. 42% chance. 42% chance that you'll have 1, 0, 1, or 2. So now you can deal with that, right? Food's not out there yet?
No.
All right, when it comes. I'm hoping to get to a good spot. So now you can use the statistics to calculate the average number of people waiting, the average number of customers that are in the system. They've done that mathematically. I don't think we need to drive that. It's just, you know, hey, you got your arrival rate, you got your service time, and that's going to affect how many are waiting. That's going to affect the total number that's in the system. And there's a nice table in your book that summarizes it for different cases in this section. And there's a nice table that shows you, as a function of arrival rate, how it looks, the lambdas. Got the average time you spend in there and the average time in the system. So you got average time waiting, average time in the system. So we can just plug into these formulas if you want to use them. So based on our lambda, which was, oh, they've changed it. Oh, gosh, we'll see what it is at now. Yeah. Formulas, be consistent. Now lambda is 4 customers per minute, and your mu, your service time, is 5 minutes. So now they're going to say, well, how many, what's the average number of customers waiting? 3.2, you just plugged it in, right? 4 squared, 5 times 5 minus 4, 1, okay. Obviously you get bad things if you got arrivals coming quicker than your service. You know, formula doesn't work well. Average number in the system, 4 customers, and they can just calculate the average waiting time and the average time spent in the system. Nice little calculation. I think, let's see, they do. Oh no, yeah. The book looks at this as you get closer and closer to, as your arrivals get closer and closer to your service time, and you can see how the average time starts getting really bad. I mean, obviously, look, if these two are equal, your average time spent in the system goes to infinity. You know, starts getting up there, and so the closer they get, the worse things happen. And so, you know, you can see how mathematically that works. All right, so let's see. Little's Law, they only do a few view graphs on it. I don't want to spend much time on it because you did it. I think you probably didn't express it this way, right? Did you have throughput? They're expressing as the number in the system, the rate, and the time the unit spends in the system. Same equation, same thing. You can turn it whichever way you want, where you can look at what's your throughput coming out, and how your inventory, yep, and your throughput time. There it is, yeah. So that's probably what you mostly solve for. Yeah, throughput rate and throughput time. But they use it in an example. So they've got a manufacturing plant. You've got 100 a day coming in. You can process on average 25 orders are in the system at any point in time. You go up to Work Center A, the inventory is 14 on average. Work Center B, the inventory is 1.5, and you got 70 coming out a day here, 30 coming out a day there, and they're just going to apply Little's Law to come up with your throughput. And other questions. How long does an order A or B stay in the processing area? How long does it take through the A path to work, through the B path, and what's the average time? Okay, so you'll see how they'll do it. So the throughput, just using little laws, 25 in the front end divided by 100 per day. So there's 0.25 days are spent in the processing. A, you had 14 was your inventory, 70 per day coming out, so 0.2 there. B, they didn't even calculate, did they? Let's see. So A's total time is how much it sits in processing, plus how much it's set in A itself. What does they do B on the next slide, I think, yeah. Sorry about that, I think, yeah. So B was, they didn't calculate it, there it was. So now, the average time that they spend in the plant, the A path and the B path, and the percentage of items that go through each pass, and you can calculate it this way, or look, something interesting, they looked at the percentage of the orders coming out and did it that way. Yeah, interesting way to do it. Yeah, I like that. So anyway, you guys have looked at that before. So now the case study is the coffee people. Let me do it. Yeah, I don't want to do real long, really, because you guys didn't. Should we go ahead and take a break anyway? It's been an hour. I notice the people getting up and going to the bathroom. I won't do the fish market too much.